In this video, I'm going to go through a method on how to derive SALCs. What we're going to use are projection operators. The systems that we'll be examining will be the hydrogen 1s SALCs from water, which is in C2v Symmetry. We're then going to go a little bit more complicated and look at the hydrogen 1s SALCs from the equatorial ligands in a molecule in C4v Symmetry. So I'll show you how to develop SALCs for a molecule that has a doubly degenerate representation. We're then going to expand this and go more complicated, derive the hydrogen 1s SALCs from ammonia, so a molecule in C3v Symmetry, where we'll have to deal with a doubly degenerate representation again, but it's more complex than the molecule that's in C4v Symmetry. And then finally, just how to derive the SALCs for p orbitals in a molecule in C3v Symmetry. Now, I'm not going to go through and define formally what a projection operator is. So we symbolize a projection operator with a p and a hat and then some function. Okay? This means that we're performing a projection operator on some specific function. And for our purposes, we're going to think about these projection operators as tools in which we will project out wave functions from some basis function. And these basis functions will either be an atomic orbital from one of the ligands or a linear combination of a select set of atomic orbitals. To set up what we're going to be doing, what we're going to do is we're going to generate different wave functions, psi sub I. These wave functions transform as some representation I of group G. The wave function is going to be proportional to a projection operator, P sub I, operating on some basis function. This quantity is in turn proportional to the following sum. Here. What this sum contains is the character for each operation J in representation I, and how the basis function transforms upon performing that operation. The general method that we're going to go through to use these projection operators to form SALCs is to first identify the molecular point group and your symmetry equivalent ligand atoms. The second thing is we're going to form a reducible representation, gamma R, of orbitals from those ligand atoms that reducible representation is then going to be reduced into its composite representations from the group. We're then going to pick one atomic orbital in most cases. Sometimes we're going to be generating linear combinations and using those. And we're going to see how does this atomic orbital transform after doing each operation that defines that point group. We're then going to multiply through by the character for those various operations, and then sum and combine like functions. Steps 4 and 5 correspond to performing that projection operation for that given representation. And then finally, 6, we're going to normalize the resulting wave function. We're going to start by generating SALCs for the hydrogen 1s orbitals in water. Water is contained in C2v Symmetry, and I'm just going to put it in an axis system so that we can define our operations. So there's our z-axis, and then the y-axis is going to go this way. Now what we need to do is we need to create a reducible representation of our hydrogen 1s orbitals. So I'm just going to draw our 1s orbitals, and I'm going to label them 1 and 2 so that we can see how they transform under the operations of this point group. So C2v has an E, a C2 axis, a sigma v that's contained in the xz plane, and a sigma v prime that's contained in the yz plane. E, both of these hydrogen 1s orbitals stay in the same place, so that gets a 2. Upon doing that C2 rotation, 1 converts to 2, 2 converts to 1, so that's a 0. None stay in the same place. The same for the sigma v. None of those stay in the same place when you reflect through the xz plane, while both hydrogen atom 1s orbitals will stay in the same place when you do the sigma v prime, the yz mirror plane. So this is our reducible representation for the hydrogen 1s orbitals. And when we reduce this reducible representation for the hydrogen 1s orbitals, we get one A1 representation plus a B2 representation. And because reducing representation is going to be important for generating these projection operators, I highly recommend you go back and review how you go through and you reduce representations in a point group. Now, what this representation means is that we're going to have one SALC of hydrogen 1s orbitals that's going to transform with A1 symmetry, and we're going to have another SALC that's going to transform with B2 symmetry. In order to determine what these SALCs look like, what the mathematical form of those SALCs are, what we need to do is we need to apply the projection operators of an A1 on some basis function. And the basis function that we're going to pick is just the 1s orbital corresponding to hydrogen 1. So we're going to project out SALC A1 by performing a projection from that particular hydrogen 1s orbital, and we're going to do the same thing with the B2 representation. Before we go through and do this, we have to know how that hydrogen 1s orbital from H1 transforms under each operation of the group. So how does sigma 1 transform on E, C2, sigma V, and sigma V prime? E, that 1s orbital from H1 stays in the same place, so it remains a sigma 1. Upon doing a C2, sigma 1 converts to sigma 2 converts to sigma 1, so it changes to sigma 2. Sigma V, it's going to reflect, so we get a sigma 2. Sigma V prime, it stays in the same place, so it remains sigma 1. So just rearranging those to give us a little bit more room. What I've done with the transformation of the hydrogen 1s is the first part of that projection operator. Now we're going to go through and we're going to consider how the various operations transform under the given representations. So we're going to complete the projection of A1 on the hydrogen 1s orbital from H1. So with the A1 representation, E has the character of 1, C2 has the character of 1, sigma V has the character of 1, sigma V prime has the character of 1 is the totally symmetric representation. So we're going to be multiplying these functions that we generated here by the corresponding characters and summing those together. So what we get is 1 times sigma 1 goes to sigma 1 plus 1 times sigma 2 goes to sigma 2 plus 1 times sigma 2 plus 1 times sigma 1 sigma 1. So combining like terms, this goes as 2 sigma 1 plus 2 sigma 2, which reduces down to sigma 1 plus sigma 2. This means is that the A1 SALC is going to be equivalent to sigma 1 plus sigma 2. And just to point out, this wave function here is not normalized. We're going to go through the normalization procedure in a second. So now we're going to go through and we're going to finish the B2 projection on the hydrogen 1s orbital from H1. E has a character of 1 under the B2 representation, C2 minus 1, sigma V minus 1, sigma V prime 1. So we have sigma 1 plus negative sigma 2 because we multiplied sigma 2 times the character for C2 minus 1 plus negative sigma 2 plus sigma 1. So the projection of the B1 representation from sigma 1 is going to equal 2 sigma 1 minus 2 sigma 2, which is equal to sigma 1 minus sigma 2. So the B2 representation yields the wave function for the out-of-phase combinations of the hydrogen 1s orbitals, sigma 1 minus sigma 2. We now need to go through and normalize these wave functions. So what we're going to be doing is putting a normalization coefficient in front of these. And the normalization coefficient is equal to 1 over the square root of the sum of the individual atomic orbital coefficients, Ci squared. So in the case of Psi A1, that's going to be 1 over root 2 sigma 1 plus sigma 2. This is going to be 1 over root 2 sigma 1 minus sigma 2. We can now go through and draw out what these are going to look like. So here, the A1 SALC has these in phase, and the B2 has these out of phase. So what's going to happen is the SALC that has A1 symmetry is going to combine with atomic orbitals that have A1 symmetry. So under C2v, this is going to be your s orbitals, your pz orbitals. If this were binding into an atom that had available d orbitals, you would also have your dz squared binding into that SALC. In the B2 representation, you would combine in your py type orbital because the py transforms as the B2 representation under C2v symmetry. In addition, you would have other orbitals if your atom had those energetically available to combine with this B2 rep, such as your dyz and your dxy type orbitals. We're now going to move on to a slightly more complicated example, and that's the hydrogen 1s SALCs in a molecule under C4v symmetry, focusing on the equatorial atoms in that particular type of molecule. So this has C4v symmetry. And we're going to examine this looking down the z-axis. With our hydrogen 1s orbital indices labeled like that. So this is under C4v symmetry, and we need to generate our reducible representation for the hydrogen 1s orbitals. So for the C4v point group, we have an E, we have two C4s, we have a C2, we have two sigma V's, and we have two sigma D's. Going through and generating the reducible representation, we get a 4. All the hydrogen atoms stay in the same place. A 0, doing a C4 rotation, changes the position of each one of those hydrogen 1s orbitals. Doing the C2 does the same thing, they all change. The sigma V, and we'll look at a sigma V along that bond there. When you do that sigma V, the sigma 1 and the sigma 3 stay in the same place. 2 and 4 convert, so we have a 2. And then the sigma D, so the sigma D going along that way, we get a 0. And so this reducible representation for the hydrogen 1s, when you reduce this down, you get an A1 plus B1 plus an E representation. And what we're going to do is we're going to project out by focusing on this hydrogen 1s orbital here from H1. So what we need to do is we need to determine how every single one of those symmetry operations changes H1. So we can no longer work with just one operation in each class. So with sigma 1, with an E, it stays in the same place. So it's sigma 1. With a C4, this rotates into your sigma 2. So goes to sigma 2. With the C4 cubed, the other member of that class, it rotates all the way over to sigma 4. C2 rotates to sigma 3. Sigma V stays in the same place. Sigma V prime along that axis, it reflects to sigma 3. Sigma D goes into sigma 2. And sigma D prime, that's that mirror plane there, it reflects there. So this is how sigma 1 changes for each operation in that point group. We're now going to go through and finish the projection for the various irreducible representations that made up the reducible representation of the 4 hydrogen 1s SALCs. We're going to start with A1, just multiplying the basis function sigma 1 through by the characters for each operation. And remember, the character for each element in a class is going to be the same for that given irreducible rep. For the totally symmetric representations, these are all 1. So when we go through and multiply through, you get a sigma 1 plus sigma 2, sigma 4, sigma 3, so this is going to equal 2 sigma 1, 2 sigma 2, 2 sigma 3. We can reduce this down and normalize the wave function. So the A1 is going to be 1 over 2, so 1 over root 4. And we get this for our A1 SALC. We're now going to go through and project this through for the B1 SALC. So it's a sigma 1 minus sigma 2 minus sigma 4 plus sigma 3 plus sigma 1 plus sigma 3 minus sigma 2 minus sigma 4. Gathering together like terms. 2 sigma 1 minus 2 sigma 2 plus 2 sigma 3 minus 2 sigma 4. So we have that common 2 terms. This is approximately equivalent to sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. So the normalized wave function for the B1 SALC is 1 over 2, so 1 over root 4, sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. We're now going to go through and project out the SALC for E using the sigma-1 as our basis function. So characters E2, C2 is -2, and then the C4s and the mirror planes all have characters of 0. So this is going to simplify going through and doing this. So what we get is 2 sigma-1 minus 2 sigma-3. So the projection that we get is this, and the wave function is going to be 1 over root 2 sigma-1 minus sigma-3. E is a doubly degenerate representation, which means there has to be another function that goes with this E SALC that we just derived. So we're going to call this EA. There's a few different ways in which you can get your degenerate SALCs. The way in which we're going to use is we're just going to project again onto an atomic orbital that's not contained within this function here. We're going to project onto sigma-2. When you do these projection operators, you'll either, and you get valid wave functions, you'll either get out the same wave function by projecting onto a different atomic orbital or its partner wave function in this case. To get that other member of the E representation, we now need to go through and project on a different basis function. So we're going to just project on the hydrogen 1s orbital from hydrogen 2. So doing an E, it remains sigma-2, C4, sigma-3, C4 cubed, sigma-1, C2, sigma-4, sigma-v, sigma-4, sigma-v prime, sigma-2, sigma-d, sigma-1, sigma-d prime, sigma-3. I've simplified the table here to just reflect that we only need to concern ourselves with the E and the C2 operations because all the others have characters of 0. So multiplying this through, we get 2 sigma-2s minus 2 sigma-4s. So projecting through E on sigma-2, we get this. Going through, the other wave function in the E representation is 1 over root 2 sigma-2 minus sigma-4. We're going to go through, when we go through the C3v point group, to point out something, but just to make a note, these are valid wave functions for this particular set of orbitals under this symmetry because these two wave functions are orthogonal to one another. We're going to go through and see how you can determine whether or not they're orthogonal or not, but just to point out these two are orthogonal. Now just going through and summarizing our results, we have the A1 representation, or the A1 SALCs, these are the in-phase combinations. Those look like that. The B1 are the out-of-phase combinations. So you have that. with nodes there and there. So a node and a node. We derive the two SALCs of E symmetry. And so these look like this. And that. So just a note, sometimes you'll see SALCs for these types of point groups, for your E-type SALCs, that instead of looking like these, will be these. So these SALCs here are equivalent to these SALCs here and are valid ways of representing the E-type SALCs from the hydrogen 1s orbitals. These were formed using different basis functions. These were formed using a basis function that was made from the linear combination of sigma 1 and sigma 2. We're going to see how we can use these and the results that you get and why you would need to use those when we derive the SALCs for ammonia under C2v Symmetry. That will be tackled in part B of this video.